Okay, this is sample problem 14.2. It says in here to consider the reaction 4NO2 gas plus O2 gas to form 2N2O5 gas. At a particular time during the reaction, nitrogen dioxide is being consumed at the rate of 0.00130 molarity divided by seconds. At what rate is molecular oxygen being consumed? At what rate is dinitrogen pentoxide being produced? Okay, so this is all about the coefficients. The coefficients should be the first thing you look at when you see a question where they're asking you to find the rate of change of one substance and they gave you the rate of change of another substance. So take a look at it. What are they telling you in this problem? Nitrogen dioxide is being consumed at a rate of 0.00130 molarity divided by seconds. That's your given information. So the next thing you have to do is you have to look at that equation and figure out what is nitrogen dioxide. There are three choices, right? It's either NO2, it's O2, or N2O5. Which one do you think it is? Which one is nitrogen dioxide? Is it O2? Is it N2O5? Or is it NO2? Take a look and see. The next thing you want to do is you want to write that information down. So let's go ahead and put it down. The nitrogen dioxide, so I'm going to write it this way. The change in the concentration of nitrogen dioxide divided by the change in time is, now here you have to be careful, it's being consumed. When something is being consumed, the change is negative because the amount of it is decreasing. It is not going to give you the sign in this problem. You have to figure out what the sign is. It's being consumed, so that's negative. Negative 0.00130 molarity divided by seconds. Okay? So change in the concentration of NO2 divided by the change in time. Now, how did I know it was concentration? I looked at the units. Molarity is concentration, so that would be the change in concentration. The units of time, what are they? Well, it says molarity divided by seconds, so the unit of time, therefore, is seconds, okay? So now what I'm going to do to answer the two questions is I'm going to do this pretty formally because I want to make sure I get it right. The first thing I'm going to do is I'm going to find the rate of the reaction. Okay? And so what I'm going to do is I'm going to say, okay, the rate is the negative change in the concentration of NO2 divided by 4 delta T. Okay, so that's from sample problem 14.1. So if you don't know where I got that from, you have to go back and redo sample problem 14.1 because that's where I discuss it. If you look at the rate is divided by 4. We don't have divided by 4 up here. Okay, so if I want to know what the rate is, I just need to take this and divide it by 4, right? This expression right here is identical to this one except for the 4. If I divide this one by 4, that's going to give me the rate of the reaction. So let's find the rate. We're going to divide it by 4. So it would be minus 0.0130 molarity over seconds divided by 4. Now, why am I not putting delta T? Well, delta T is right here. This is the delta T right there, divided by seconds. That means divided by delta T. So now we've got a little division. We have a little arithmetic to do here. So 0.0, I forgot to put a 0 in there. There's 2 zeros in there. You have to be very careful about these rate law problems or these kinetics problems, there's zeros all over the place. And you have to be careful you get the right number of zeros. So let's make sure we have the right number of zeros. It's 0.00130, right? So 0.00130. So I'm going to write that out, calculate that out, and now you're going to get a really small number. So it's so small that it needs to be in scientific notation. It's just too small to put zeros in anymore. Okay? So that's the rate. Now that's not what's being asked, but I'm going to do that as the first step because I can now figure out how oxygen and how dinitrogen pentoxide are related to the rate. You see, the rate is also equal to the negative change in the concentration of O2 divided by delta T. So that means this right here is equal to the rate. I already figured out what the rate is right there. So that means that for O2, there you go. Right? I'm using a substitution here. If I calculate the rate, and then when I do this problem, I say, hey, the rate is the negative change in the concentration of O2 over delta T, that's equal to the rate, then these two are equal to each other. This is equal to each other right there. So that we've got the part A done. Okay? So what does that mean? What that means is the change in the concentration of O2 is actually quite a bit, so it's quite a bit smaller, lower than it is for NO2. Let me put this one in scientific notation over here. It really should be. I don't know why the authors didn't put it in scientific notation. Oops, that's a -3. So this is the change in concentration of NO2. This is the change in concentration of O2. It just happens to be equal to the rate. Now, why is there a difference? It all comes down to the coefficients. Because there's a 4 in front of the NO2, it's going to be consumed faster than the O2 is. Now that might not seem intuitive. You might think, wait, they're going to get used up at the same rate. No, that's not true. They don't get used up at the same rate. If you imagine this, imagine I had a pile of wheels and I had a pile of bicycle frames and I started assembling bicycles. Every time that you made a bicycle, you would only use one frame, but you would use 2 wheels. So the wheels would be consumed more rapidly than the frames of the bicycle would be. And that's what this calculation is showing us. It's showing us that the oxygen is going to be consumed more slowly than the NO2 is because of the 4 in front of the NO2. Now let's try the last one. The last one is N2O5. So let's write the rate in terms of N2O5. Well, N2O5 is a product, so if there's no negative in front of the rate, right? We learned about that in sample problem 14.1. So it's just the change in the concentration of N2O5 over the change in time. However, remember the coefficients? There's a 2 in front of it, so we put that down there like that, okay? So now, how do we figure out what the change in concentration of N2O5 is? Well, we know what the rate is, right? The rate is the negative of the negatives, so that's 3.25 times 10 to the minus 4. Remember, the rates are actually always positive, so if this is negative here, the rate is the negative of that negative, so that makes it positive. So technically it's positive. But the O2 has a negative in front of it, so it's going to be negative. N2O5 is a product, so it'll be positive. Now, we know what the rate is. The rate here is 3.25 times 10 to the minus 4 molarity per second. So how do we find the change in concentration of N2O5? Well, we just use a little algebra. if this ratio right here is equal to this number right here, and we just want to find the change in concentration over the change in time. We just want that part of it. What do you do? If I told you this, you have x over 2 equals 3, and I want you to find x, what would you do? You'd multiply both sides by 2. And then that would give you x equals 3 times 2, which is 6. So same thing here. We want the change in concentration of time over change in time. We want that. We don't want the 2, so we multiply both sides by 2. So we multiply this side by 2, we multiply this side by 2, and you get 6.50 times 10 to the minus 4 molarity per second. And there you go. There's your final answer. This is the change in concentration of N2O5 divided by the change in time. The change in concentration of O2 over the change in time, that's going to be negative. The change in concentration of NO2 over the change in time, that's also going to be negative, right? They're changing in a decreasing way. Decreasing, if something decreases, that's a negative change. If something is increasing, that's a positive change.